I'm happy to kind of talk about our work on crosstalk attacks and crosstalk vulnerabilities in cloud-based quantum computers. I think maybe much less hands-on than the motorcycle, but I think part of the goal here is to also give some motivation for the community to start looking at quantum computers, which are not doing much right now, but they're already quite easily available, and you can access them, and you can actually experiment with them. So maybe just as a motivation, why are we looking at quantum computing? And as maybe you're familiar, every few months or even more often, there's a lot of announcements from different industries, different companies that are showing off their latest quantum processors. And as we can see, there's a lot of huge investment by not just IBM, but many other companies that are building these machines. And these machines are actually getting better and better as time progresses. These are sort of different roadmaps from the companies, and maybe this one, every company has a roadmap to show where their quantum computers are going. But I think you can kind of think of today, for most of the machines, we're in the range of about 100 to 200 physical qubits that are accessible, and then this is either Quantinuum or Rigetti, IBM, all different companies are roughly in the same range. And 100 to 200 physical qubits doesn't really let you do much computation, but it's actually kind of steadily increasing. So we've gone from about 5 or 7 qubits 6 or 7 years ago to 100, 200 qubits, and all these roadmaps are sort of projecting thousands of physical qubits in the next few years. So these are, of course, roadmaps from the companies, but I think they're pretty much on target, and some things that they publish, sort of internally, they're probably more advanced than they're actually saying, so they kind of meet the targets. And our special interest is on hardware security, but really from the perspective of a cloud-based deployment. So the idea here is, what are kind of the vulnerabilities when the user is accessing a quantum computer, but they're not controlling it physically? And for the near future, and probably for the far future, most of the quantum computers will be available from different cloud providers, AWS, Microsoft Azure, IBM, they all have cloud-based access to different machines. Of course, IBM makes access to their own machines. Amazon and AWS make access to different machines from other providers. But kind of interestingly, all these other providers, maybe not all of them, but a lot of them have their own cloud. So for example, you can, I guess it's not shown here, but you can go through Amazon to access a Rigetti quantum computer, but Rigetti itself has its own cloud. So there are many different ways to access these machines remotely, and unfortunately, or at least presently, there's really no security features in these deployments. The cloud, the networking, of course, is encrypted. The cloud environment has standard protections, but once you start interacting with the quantum computer, or once you start sort of loading circuits on the quantum computer, there's basically no security checks or no really strong security features. And again, as a bit of a motivation, quantum computing is becoming quite a big ecosystem. This is actually maybe a year or two old picture, but it's not just IBM and few people making quantum computers. There's a lot of companies, like Wells Fargo, JP Morgan, AstraZeneca, all these companies who do not own quantum computers, but they're developing quantum algorithms. They're trying to build quantum algorithms, and then that's kind of one of the motivation for the research on the security is there's a lot of intellectual property and proprietary data that will be executed on the quantum computers. So this is sort of, unfortunately, gives attackers some motivation. We, of course, have the actual QPUs, or quantum processing units, so all these different companies, and they have some intellectual property in the hardware design. They want to prevent reverse engineering. There are different, maybe even possibilities of hardware trojans. Today we'll talk about more on the sort of hardware type attacks with the crosstalk, but there's a lot of security issues and concerns for the for the manufacturers. And I think one very interesting part that we're starting to look at more now is, when you think of a quantum computer, you think, some exotic qubits, but actually I think sort of maybe even by volume, the biggest part of quantum computing is all these classical hardware that's actually controlling the quantum computer. So you have some famous companies like Bluefors that make these fridges, but Keysight was here. Keysight makes a lot of controller equipment. There's a lot of really classical equipment that's driving these quantum computers. So maybe they're not quantum specific things, but I think there's a lot of security vulnerabilities and security sort of targets in the classical equipment, and kind of everybody here is really familiar with all these classical attacks. So in this talk, I'll focus mostly on this on the QPU part, but the ecosystem is quite big, and I think there's a lot of vulnerabilities. So if you've seen some of my talks, I keep reusing these figures, so sorry if somebody's seen it, but I think this kind of gives you a good overview of what a typical quantum computing system is. And in the figure, sort of on your far right, you have the actual QPU, or the quantum processing unit. For superconducting qubits, you'll see these, the chandelier, the fancy fridge that holds the qubits. But that's really just one part. Really, I think the heart of a quantum computer, which we'll not talk about today, but is really the quantum computer controller. So there's a whole rack or sets of racks of classical signal generators, mixers, other equipment that's actually driving the qubits via different, typically analog signals. And then if it's a cloud deployment, this connects to some management server, and then you have the users actually accessing these machines remotely and loading their quantum circuits. So considering different attacks, today we'll talk about attacks on the QPU, which is where the actual computation is being done. But there are many different kind of threat possibilities, or sort of the attack surface is quite big. I think quantum computer controller is something we're exploring these days, is very prominent. But I know also the communication. I think one interesting thing is that a lot of these quantum computers are driven by analog signals that are actuating the qubits. And as much as you can encrypt everything going up to the controller, whatever comes out of controller is analog signals that cannot be easily encrypted. So then if somebody is able to spy or modify the analog signals, you can directly kind of intercept, like in the motorcycle example, you could put some sort of a harness in between the controller and the QPU, and you can sort of intersect exactly what's driving the qubits, or what's being read out of the qubits. And for certain types of quantum algorithms, you do a lot of classical optimization on GPUs to optimize the parameters of the circuits. So somebody could actually extract a lot of information about the quantum circuits from the optimization algorithms running on the classical coprocessors or GPUs. And I assume that the middle part of the cloud is already secure, but then you have the end users where, of course, the quantum programs could be malicious. So when I talk about the crosstalk, we'll kind of touch upon the quantum programs being malicious and causing this crosstalk, but also things like compilers. What if the compiler sort of steals some of your proprietary circuit as it's being compiled? So today we'll talk about the QPU, but there are many other interesting things that I hope, if anybody's interested, please reach out. We're trying to grow a community around sort of securing, first attacking, but then really securing the quantum computers. And as a very brief aside, we have cryptography, we have, cryptographic hashes for integrity. So, some limits of protections with ciphers and cryptography is that, you can pretty much protect all the classical part, but then things like the QPU you cannot protect with the encryption. The analog signals cannot be protected with encryption. Some of the, maybe should be in orange, some of the compilation or the optimization could be protected with fully homomorphic encryption, but that's not really practical. So you can see that the closer you get to the quantum computer, the harder it is to protect it with existing methods. And same for integrity. You can do all the integrity checking you want on the network packets, things like that. But once you get to the, for example, how do you integrity check analog pulses going to the QPU? That's kind of a really, really open question. So, so I hope that kind of this motivates again kind of really focusing on the controllers and the QPU. So we're really going to focus on the crosstalk attacks and vulnerabilities in the QPU. And I should say actually that I guess I'll repeat it when I get to it. But what we've been experimenting is actually done on real IBM machines. So thank you to IBM for giving us and a lot of researchers access. So a lot of you'll see some small quantum circuits later, but this is done by actually connecting to an IBM machine, executing some circuits, and collecting data out of it. So it's really not simulation, but really on IBM machines, and you can extend it to other types of machines. So before I talk about the attacks, I thought to give just very brief introduction to qubits and quantum circuits, just to provide a setup for how the attacks are generated, or how the vulnerabilities are triggered. So as a very brief introduction, maybe you've seen this notation somewhere before. So when we talk about quantum computing, we have qubits. Typically, we have most of the systems are what's called a two-state quantum mechanical system. You can basically think of it that each qubit has two basis states. So like ket 0 could be like a lower energy state, and ket 1 could be like a higher energy state, or it could be something being polarized or spin up or spin down. So you have to have some physical property that represents that is the two different states, and then your qubit or quantum bit or quantum register is basically that physical state holds the qubit, and each qubit is basically in the dependent on these basis states. And there are a couple of properties of qubits that you probably heard about that kind of sort of give the computational benefit to quantum computers. So I guess the most famous one is superposition. It's basically the idea that for n qubits, they can all be in a superposition of up to the 2 to the n state. So at any one time, the qubit is not in one state, but in any superposition of those states. And so for one qubit, you have two possible states, 1 or 0, but each of the states is associated with this alpha and beta, which is the probability amplitudes, and then these are probability amplitude squared gives you the probability. So at each time, the qubit could be in 0 state, could be 1 state, or could be sort of 25% 0, 75% 1. It could be any combination. And then if you extend it into like so 2 qubits, then you have 4 basis states, 0, 0, 0, 1, 1, 0, 1, 1, and you can have different probabilities. So basically, the qubits are able to contain sort of this superposition. And the next one is entanglement. Is basically when you entangle qubits, reading sort of the behavior of one qubit becomes correlated with another qubit. And I think the most important, which I think people don't talk about it as much, is actually the interference. So qubits basically represent waveforms, and they can interfere with each other. And then, so if you have n qubits in 2 to the up to 2 to the different possible states, it's not really useful. The end goal really of any quantum algorithm is to sort of through the interference, through distractive or constructive interference between the waveforms, to really get you to one specific state, which is the solution of the algorithm. So this is the magic. I don't understand of how people design quantum algorithms, but if you do it, so there's lots of opportunities. But really the key is to use the interference and superposition entanglement to get your solution. So that's what, when you come up with a quantum algorithm, you are using these properties. And I mentioned that the qubits are implemented using different physical means. The two main ways of implementing qubits is either, they call it manufactured qubits. So we'll talk today about superconducting qubits, where you manufacture a circuit, a physical circuit that's manufactured using CMOS technology that's used to create the qubit. Or you could have things like trapped ions, where each qubit is really a physical particle. So there's a lot of interesting things to consider, that if you manufacture qubits, they're not all identical. They have many problems. If you have things like trapped ions, each qubit is an ion. It's by nature identical, so there's many less problems. But sort of from the CMOS, or from a hardware manufacturing perspective, a lot of people are much more familiar with designing CMOS circuits, so superconducting architectures are dominated, although there are many, Honeywell or Quantinuum these days, and IonQ are other types. So in this talk, we'll talk about superconducting qubits, and some of the crosstalk issues are specific to the superconducting qubits. Other architectures like trapped ions may behave less crosstalk issues, but they might experience different types of noise and faults when you're interacting with the qubits. So so we'll focus on superconducting qubits. And another picture maybe you've seen. So when you have a quantum computer, especially a superconducting quantum computer, you usually see a picture like this that shows the topology of the machine. So in these pictures, basically each dot or whatever, or circle, is a qubit. So for example, this is a 127 qubit machine from IBM, and for whatever reasons, this is the topology that they connect their qubits in. Google has sort of slightly different topology, but in all of these superconducting machines, you have this fixed topology because somebody is fabricating these Josephson junctions, these physical qubits on the chip. So you have the circles that are basically the qubits, and then each line represents a coupler, which is basically needed to perform operations. So we'll talk in the one slide or two. Whenever you want to do some computation, you perform a gate operation on the qubits, and either you have a single qubit operation or a 2-qubit operation. And if you want to perform a 2-qubit operation, the qubits that you're operating on have to be adjacent, or they have to be connected by a coupler. So one limitation, for example, of like an IBM type machine is that you can perform an operation between qubits 0 and 1, but you cannot perform an operation between qubits 0 and 2. So if you want to perform an operation between qubits 0 and 2, first you have to swap the state of, let's say, 1 and 0, and then you have 1 and 2 are able to interact. So there is sort of this constraint that any computation has to be done among the qubits that have a physical connection. And one reason for the reason you don't have more connections is that this is a planar 2D CMOS chip, and I cannot, at least currently, people don't have sort of 3D connections. Although that's pretty active research area. How do you kind of increase the connectivity? So this is kind of the setup for the physical layout of the quantum chip, and then each qubit is one of the Josephson junctions. So again, a very brief introduction to sort of quantum states and quantum gates, just to get into actually the end goal is to actually show this block diagram, this picture. So whenever you have in a quantum computation, sort of it's not like in a regular processor where you send some data to the CPU to operate on it. Instead, you have the qubits. So in these circuit diagrams, so this would be called a quantum circuit. So in circuit diagrams, each line represents one of the qubits, and then the time progresses from left to right. So as your circuit executes, each of the qubits is actuated on by the square represents a quantum gate. And typically we have 1 or 2 qubit quantum gates. You could have bigger ones, but they're difficult to implement. But the main idea is that you have, I mentioned before, you have the side, you have some state of the qubits. So that's sort of the state of the qubits. Then you actuate the qubits, and you get to a new state, and kind of this repeats itself. So you can perform the computation on the qubits. And in the end, if you remember one thing about quantum circuits, maybe remember a figure like this, that basically to perform quantum computation, a user designs a quantum circuit that's composed of a number of qubits. This is sort of limited by up to the physical number of qubits in your machine. Then you execute the circuit by basically applying different quantum gates to those qubits as time progresses, and then finally at the end you perform measurement. And so when you perform measurement, you actually get the classical ones and zeros, which is the result of computation. And that's how pretty much all the quantum circuits execute, regardless of the superconducting or trapped ion. How you implement the gates is very specific to the type of a quantum computer, but that's kind of the main structure. Okay, all right. So with that picture in mind, so now getting to crosstalk vulnerabilities in quantum computers. So we have this picture that when you execute a quantum circuit or a quantum program, you just apply gates to the qubits, and ideally there's no noise, there's no interference, there's no nothing problematic. But unfortunately, today we're in what's called a noisy intermediate scale quantum NISQ era, which means that the qubits are and the quantum gates are very noisy. So I didn't highlight it, but maybe on one of the first roadmaps, or you saw that the error rates for the quantum gates are on the order of 10 to the minus 4 and 10 to the minus 5. So these are pretty good, but they're not perfect gates. So it's sort of every time you execute the computation, it might not be performed perfectly. And that's actually a separate issue why you have to run quantum circuits many times today to kind of average out and get the outputs. But considering the crosstalk, this is actually what the attacker can exploit, is these imperfections in the quantum circuit. So there are many imperfections. The qubits themselves, they decohere, they lose their state over time. The gates, like I mentioned, 10 to the minus 4, 10 to the minus 5, they're not perfect. So every time you execute gate, it may or may not work, which is problematic. And another interesting thing is that when you execute a gate on a set of qubits, that actually might cause some noise and interference on the adjacent qubits through their I'm not a physics expert, but there are many different mechanisms that, especially in superconducting qubits, these are Josephson junctions are made of capacitors, inductors, other types of electrical elements, and anytime there's some parasitics, there might be some coupling through the substrate. There are different sort of electrical means for one qubit to interact with another qubit unintentionally, and that creates noise and interference. And very sort of also when you read out the qubits at the very end, actually there's interesting what's called a readout crosstalk, that reading one set of qubits actually might affect what you see on another set of qubits. But where this work on crosstalk goes into actually what happens if you actually have multiple circuits executing on a single quantum computer. So since quantum computers are very still rare and sort of expensive, there's a lot of sort of research and proposals for having multiple users or multiple circuits running on the same quantum computer. But then what are the security implications? And as you can see from this picture, if there is interaction between gates of one circuit, if you have multiple circuits running on the same quantum computer, they will also be interacting. And then this is actually how we're exploring how can you exploit that interaction as a security attack, which this is sort of basically so if you remember anything, this is the picture of the crosstalk. One circuit executing next to another circuit through the substrate of the superconducting chip can cause crosstalk that affects another circuit. So coming back to our picture, if you have a quantum computer made of some number of qubits, then if we have multiple users running on that quantum computer, it basically means that different qubits are assigned to different parts of the quantum computer, and we're sort of trying to understand what are the sort of the different security implications or attacks, and how can they affect the qubit. So if you did any or if you're familiar with any work on FPGA security and then sort of crosstalk attacks in FPGAs, this is not unlike that if you want to have like a mental model. So getting to demonstrating some actually results. So all of these different results from our research group, but also from other research groups, are mainly collected on real IBM machines. So this is data and graphs from running circuits on IBM machines. And some of the very first work on crosstalk, it's now getting a little bit old, but this was really the first demonstration of the idea. And back then, the best you could do is a 5-qubit IBM machine. This is actually the topology of the quantum computer. So now we had 5 qubits with this was the connection with the couplers. And the basis of the security analysis was basically what if we assign different circuits to different parts of the quantum computer. So let's say there's one user that has some benign circuit and another, let's call them an attacker, that has a sort of a malicious circuit. And then those are running on different parts of the quantum computer. So the typical diagram here is that you have a few qubits assigned to a victim circuit, a few qubits assigned to an attacker circuit, and they're trying to cause different crosstalk. And when the victim circuit, for example, is running like a Grover's algorithm, it should generate some output with a certain probability. So in all of the quantum circuits, depends on the circuit, but in most circuits, one of the states should have this highest output probability. That's the sort of the solution. So the solution should have some probability. But then if you run an attacker circuit, actually the output probability becomes much less, which means that you're able to disrupt the computation and sort of like a fault injection through the crosstalk to affect the computation of the victim. And sort of experimentally, we found out that executing a bunch of CNOT gates, which are these two qubit gates, seems to generate the most noise and interference. So if you make like a malicious circuit that just has a bunch of CNOT gates, which don't do any computation, but seem to generate the most noise, you can disrupt the computation of another user or another circuit. Now, although I said that there's no security features in quantum computers, they do have some basic sort of optimizations. When you compile a quantum circuit, for example, a compiler tries to remove redundant or useless gates or reorder things just to make them fit on the small quantum computer. So actually, if you submit a nonsense circuit like this with a bunch of CNOT gates, it doesn't do anything useful, and the compiler actually eliminates those gates just as optimization, not as a security feature. But thinking about some hacky ways of bypass this. For example, if you insert a small delay or another gate between those CNOT gates, that prevents, for example, the compiler from optimizing out your attacker circuit, and you still get a circuit with bunch of CNOT gates. So the end result is you have a victim that's running some quantum circuit. You have an attacker that's co-located that's running their malicious circuit, which is a nonsense circuit, but it generates a lot of noise. And the end result is basically something like this, that you, for example, in these graphs, I should have explained maybe, but so the victim has 2 qubits, is a 2-qubit Grover circuit. So there are four possibilities for the output, and in the normal case, the state 1-1 should have the highest probability. So that's the correct execution of the circuit. But then if you have an attacker, you can see that with the attack, and this is data from IBM machines, you actually get the probability of the correct solution to be reduced, while probabilities of some other solutions are increased. So in this case, you don't totally flip the solution. The 1-1 is still dominant, but you can see that you decrease the output quite a bit. And then very briefly, this can be applied to many different victim circuits. As you can see, Shor's is not included here because these machines are too small to run Shor's algorithms, so Grover's and some other ones. And you can see in all the cases, the crosstalk is able to significantly reduce the correct solution, or for the Bernstein-Vaziriani, for the last case, almost flip from 0-1 to 0-0. So through the crosstalk attack, you're able to affect the victim. And in the interest of time, I'll maybe skip this part about different types of attacker circuits. I'm happy to share the slides if anybody is interested. I did want to highlight that this is a very active area. So last year, actually, there were a number of research papers. There's one research group that sort of proposed a two-sided attack. So if anybody's familiar, of course, with row hammer attacks, now this is not unlike a row hammer attack where you have a victim qubit and you have attacker qubits on two sides, and by actuating the attacker qubits on both sides of the victim, they're able to flip the state of the victim qubit. Now, a victim with 1 qubit can't do much computation, of course, but at least the idea of the sort of two-sided attack has been proposed, and they're able to basically flip the qubits, for example, from 0 state to a 1 state, or from 1 state to a 0 state. So even though the qubit is idle, the victim is idle, by doing a lot of computation on the adjacent qubits, you are able to flip them. Another just to give you a kind of flavor of type of work that's being done, another research group has looked at this kind of exploring the crosstalk. So really I would say the fundamental reason for the crosstalk is not necessarily very well understood, but experimentally you can collect the data, and then, for example, by running on, this is part of the IBM topology, for example, you can see these arrows. So what it means, like if you run a bunch of quantum gates on qubits 8 and 9, that actually seems to affect qubits 19 and 22. They're in the topology, they're not next to each other. So through some coupling through the substrate, or some, maybe due to the layout of the qubits, even though they seem logically far apart, you can actually make them disrupt their computation. So now sort of the attacker and the victim don't have to be really adjacent into the quantum chip. Like even if you separate them, they could still affect each other. And then again, sorry, I'll skip this part. But the one thing I want to highlight, like for example, in the beginning, we inserted some delays to hide the attacker circuit. Now in this other work, they also sort of make the attacker look like a specific type of quantum circuit that naturally has a bunch of CNOT gates. So that's kind of an evolution of the different, on the attack side, you can have different attacker circuits. And then a little short on time, but last but not least, I thought this is kind of maybe a cool part to talk about, is that one thing that's specific to qubits is that each qubit operates at its own frequency. So each qubit has a unique frequency, and a recent attack that we demonstrated is, for example, what happens if you take a signal that's supposed to drive a specific qubit at a specific frequency, and then you apply it to a different qubit. So if an attacker drives their own qubits with the wrong frequency, again, it's a nonsense computation. You're not gonna do anything useful to the attacker's qubits. But the goal is to actually disrupt the qubit, the victim qubit. And the interesting result is that actually if an attacker in a faraway part of a quantum chip is able to drive their own qubits with control pulses that have the wrong frequency but match the frequency of the victim's qubits, you can actually flip the state of the victim qubit. So here are tables for, I believe, qubits 0 and 1, and you can see that if the attacker has like 20 or 30 qubits, which they're driving with the control pulse that's meant for qubit 0, then you can flip the state of qubit from if you look at the leftmost line, the blue lines, from being 100% 0 to being maybe only like 20% 0. So you're able to affect the faraway victim qubits by driving them at the wrong frequency. So maybe a takeaway message is that if you're able to collocate an attacker and victim on the same quantum chip by driving like bunch of CNOT gates to create noise, or by driving your qubits with the wrong frequencies, you can disrupt the computation of the victim and basically get them to be in a wrong state. So as maybe I'm jumping to the summary. I'm happy to take questions and have some backup slides. But maybe as a summary, quantum computers have become widely available via the cloud. There's been a lot of research last few years on these crosstalk type attacks where you're sort of abusing the noise and imperfections in the qubits to create disruptions. There was the single-sided crosstalk. There was the double-sided crosstalk, the custom pulses. I didn't get a chance to talk. There's attacks about swapping. So if you force qubits to sort of, like I mentioned in the beginning, sometimes you have to swap the qubits so you can perform operations on them because they're not adjacent. If you force the qubits to swap a lot, that creates a lot of problems. So there's been a lot of vulnerabilities. There's a number of defenses that have been proposed. We're not able to get them into commercial systems, but hopefully the industry will start getting interested. There's an idea for an antivirus type program that detects the patterns. isolating or different scheduling methods to protect the circuits as possible defenses. And just wanted to close with some future directions and one important highlight. So one important highlight, I think, is that because of the size of the quantum computers, multi-tenancy or sharing of the quantum computer is not natively supported yet. People talk about it quite a bit. There's a lot of research papers proposing different sharing systems, but at least publicly, these machines don't support multi-tenancy yet. So for all these experiments, we control sort of both the victim and the attackers under our control because we have the machine to ourselves. So the real question is, given the volume of the research on crosstalk attacks, will there be multi-tenant computers? We don't know. That's a big question. Perhaps there will not be because of security reasons. But there's also some other related things which I think is very interesting. So a lot of the quantum computer architectures are moving to like a modular or a chiplet type design, so you can fit more, you make a certain number of qubits on one chiplet and then you connect it together. So on one hand, that might create opportunity for multi-tenancy where each user gets a chiplet within a bigger chip, but then what are some crosstalk or new issues among those chiplets? So I think there's like this tension of, on one hand, we want to kind of share the machines, maximize, let's say, the revenue or sort of maximize the utility of the limited machines. But on the other hand, you have these crosstalk attacks that can be executed by one user, sort of loading a circuit that does nonsense computation, but creates a lot of noise. So thank you.